In this video, I am describing the organic chemistry chapter from modern publishers. Chapter name is Diazonium salts. Introduction. Diazonium salts, discovered by Peter Grice in 1858, constitute a very important class of aromatic compounds having the general formula ArN2 positive X negative, where X negative may be an anion such as Cl negative, Br negative, HSO4 negative, NO3 negative, BF4 negative, etc. The name of diazonium itself originated from the fact that these compounds contain two nitrogen atoms and resemble ammonium salts in certain respects. It may be pointed out that aliphatic diazonium salts, the compounds having the N2 positive X negative group attached to an alkyl radical, are too unstable to be isolated. Next topic is structure. The simplest and most important diazonium salt is benzene diazonium chloride. Let us first consider the structure of this compound as representative of the structure of diazonium salt in general. The important evidence leading to its structure may be summed as follows. Molecular formula. Its molecular formula is C6H5N2Cl. Observed behavior. First point, it is a colorless crystalline solid soluble in water but insoluble in organic solvents such as alcohol, ether. It undergoes ionization in aqueous solution as shown by the conductivity measurement of the solution. Thus, benzene diazonium chloride exhibits salt-like behavior. It undergo many substitution reaction in which N2Cl group is replaced by monovalent group such as halogen, cyanide, etc. And the next point is it undergoes coupling reaction to form azo compound such as para hydroxyazobenzene. Next point, on reduction with stannous chloride and hydrochloric acid, it is reduced to phenylhydrazine, which have the formula C6H5NH2. The last point is in alkaline solution, it forms salt known as diazotates, which exhibit geometrical isomerism and exist in syn and antiforms. Earlier formulae. First is Grice formula. The earliest structure formula for benzene diazonium chloride was suggested by its discoverer Peter Grice. In this formula, the two nitrogen atoms were directly attached to benzene in the nucleus as shown below. However, this formula was immediately rejected as it could not account for the following properties of benzene diazonium chloride. Its salt The properties are: first is its salt like character, its reduction to phenylhydrazine which contain only one nitrogen directly attached to benzene nucleus, the displacement of N to Cl group as a whole in most of the reactions, the formation of azo compound in coupling reaction. Second is Kekulé formula. Kekulé proposed the following structure in which only one nitrogen is directly attached to benzene ring. This formula could explain most of the reaction of benzene diazonium chloride, but it failed to account for salt-like behavior of benzene diazonium chloride and the instability of benzene diazonium chloride as compared to azo compounds, since both contain N double bond and linkage. And the third is Blomstrand formula and its modified form. Blomstrand suggested the following structure for benzene diazonium chloride. Supporting evidence. The above ionic structure, which is comparable to that of ammonium chloride, is supported by the following observation. First is benzene diazonium chloride is soluble in water but not in organic solvent due to its salt-like structure. Second, the conductivity of aqueous solution confirms the presence of the charge structure. Third, IR spectrum shows the presence of nitrogen-nitrogen triple bond. Fourth, it can explain all the reactions of benzene diazonium chloride. Fifth, it can explain the existence of geometric isomers of diazotates. It has been suggested that in the presence of hydroxide ion, the diazonium ion exists in equilibrium with diazohydroxide and the salt derived from it as shown below. C6H5 N positive triple bond and Cl negative. In the reversible reaction, in the presence of NaOH HCl, it gives C6H5 N positive triple bond NOH negative. Again, in the equilibrium reaction, NaOH and HCl gives C6H5 and double bond NOH, which is the diazohydroxide, and further is it formed sodium diazotate. The concentration of the different species depend on the pH of the solution. In acid solutions, the equilibria favor the diazonium ion, which while in alkaline solution, the equilibria are in favor of the diazotate. The diazotate can naturally exhibit geometrical isomerism and exist in syn and anti form as depicted below. Nomenclature: Diazonium salt are named by attaching the word diazonium to the name of the parent aromatic compound. This is followed by the name of the anion. For example, benzene diazonium chloride, P toluene diazonium bromide. Preparation of diazonium salt diazotization. Diazonium salt are usually prepared by reaction between aromatic primary amines and nitrous acid obtained in situ from sodium nitrite and a mineral acid such as hydrochloric acid or sulfuric acid at about 273 and 278 Kelvin. The reaction is called diazotization procedure for diazotization. For carrying out diazotization, the amine is dissolved in an aqueous solution of the mineral acid and the resulting solution is cooled to about 273 Kelvin. A well-cooled aqueous solution of sodium nitrite is then added slowly, uh, taking care that the temperature of the reaction mixture does not rise above the 278 to 283 Kelvin. If the temperature is allowed to rise higher, the diazonium salt form get converted into phenol. The addition of sodium nitrite solution is stopped as soon as a few drops of the reaction mixture gives a blue color with starch potassium iodide paper, indicating the presence of some unreacted nitrous acid in the reaction mixture. In other words, it shows the completion of diazotization. Since excess of nitrous acid is likely to interfere with the subsequent reaction of diazonium salts, it is destroyed by adding a small quantity of urea. Any urea left unreacted does not interfere with the reaction of diazonium salt. And 2HONO plus NH2 CONH2, it is the urea gives us CO2 plus 2 and 2 plus CH2O. The above solution containing the diazonium salt is used as such for other reactions and no attempt in is made to isolate the pure salt. This is because dry diazonium salt often undergo explosive spontaneous decomposition. Furthermore, since diazonium salt decomposes slowly even in cold solution, the solution must be used for further reaction immediately after preparation. It may be pointed out that the liberation of nitrous acid from sodium nitrite and the formation of diazonium salt require 2 molecules of the mineral acid per mole of amine to be diazotized, but in actual practice, the amount of acid used in its 3 mole. The use of excess acid is necessary to maintain proper acidity for the reaction and to prevent the combination of diazonium salt with the undiazotized amine. Precaution taken during the preparation of diazonium salt. The following precautions should be taken. First is the temperature must be carefully controlled and not allow rise to above 283 Kelvin. Otherwise, ethanol would be obtained. C6H5 N2Cl plus H2O above 283 Kelvin. It is treated and gives us phenol plus N2 plus HCl. Second is the mineral acid such as HCl, H2SO4 should be used in excess. Otherwise, diazonium salt formed would combine with undiazotized amine. Excess of nitrous acid must be destroyed. Never try to prepare pure dry salt because it is highly unstable and undergo explosive decomposition. It has a mechanism of the diazotization. It has been showed by Larkworthy that the actual mechanism of azotization depend upon the extent of acidity and the concentration of the reaction, but there is no doubt that the nucleophilic amine undergo attack by some electrophilic species such as nitrosonium ion and a positive or nitrous anhydride obtained from the nucleus acid from the nitrous acid, sorry. This one of the probable mechanism which appears to operate in many cases may be summed as follow. In the presence of strong acid, nitrous acid dissociate to give nitrosonium ion. This ion attacks the nitrogen of the amine to form an unstable n-nitro nitroso-ammonium ion intermediate. The intermediate immediately loses a proton to form an nitrosamine. This in turn undergo a rearrangement by a proton shift to form diazohydroxide. In the presence of the acid, the diazohydroxide loses water to form the diazonium ion. Aromatic amines carrying electron withdrawing substituents like NO2 on the ring are rather difficult to diazotize. This is because the electron withdrawing substituent reduce the nucleophilic character of nitrogen of the amine and thus renders it less susceptible to attack by electrophilic species. This observation also constitutes evidence in favor of the above mechanism. Diazonium salt containing anions such as Bf4 negative are generally obtained from more common diazonium salts. And the next is physical properties. Diazonium salts are generally colorless, crystalline solid, freely soluble in water. They are seldom isolated because of their instability and explosive nature. With certain metallic salts such as zinc chloride, diazonium salt form double salt, which are quite stable. Chemical properties. Diazonium salts are highly reactive compounds and are extremely useful as an intermediate in the preparation of many aromatic compounds. By the use of diazonium salt as intermediate, it is possible to introduce onto the aromatic ring substituent which are difficult to or impossible to introduce by other methods. In addition, it is also possible to introduce substituent in positions not favored otherwise in direct process. The reaction of diazonium salt may be divided into two main groups. First is reaction in which N2 is given out and the diazonium group is replaced by some other group. Coupling reaction in which the nitrogen atom are retained in the product, it is a second point. As already stated, diazonium salt are employed in various reactions in the form of their aqueous solution which are prepared just before they are required to be used. The important reaction of diazonium salt. Reaction in which nitrogen is lost as N2, the diazonium group is replaced by some other group. First is replacement of by chlorine, bromine or cyan. Its centermere reaction. A very important reaction of diazonium salt is the centermere reaction in which the diazonium group is replaced by a chlorine or bromine atom or cyanide group. The reaction is carried out by treating solution of freshly prepared diazonium salt with cuprous chloride, bromide and cyanide. Thus we have AR N2 positive X negative plus CuBr gives us ArCu and gives us ArBr plus N2 plus CuX. In case of replacement by cyanide, the diazonium salt solution is neutralized with sodium carbonate before being treated with cuprous cyanide. This is to prevent the loss of the cyanide as HCN. The mechanism of cyanide reaction is uncertain, however, a probable mechanism involving free radicals may be summed up as follows by considering the reaction with cuprous chloride. It appears that species such as CuCl2, CuCbr2, CuCN are first formed with subsequently losses an electron to form ion yield an aryl radical cupric salt and nitrogen. The aryl radical and cupric salt ultimately react to give the final product. Gattermann reaction. In a modified process known as Gattermann reaction, the replacement by chlorine bromine cyanide is carried out by using copper powder and halogen acid or potassium cyanide in place of cuprous cyanide. Synthetic utilities. Sandmeer or Gattermann reaction offer a very useful method of preparing aryl chloride and bromide in pure form. The method is preferred to direct halogenation as the latter usually result in the formation of mixture of product. Since the cyanide obtained by the above process can be easily hydrolyzed to carboxylic acid, this constitutes a good method for preparing aromatic acid. Example, oxalic acid prepared from distolene. Replacement by iodine is the second point. Replacement of diazonium group by iodine can be brought about merely by warming the diazonium salt solution with potassium iodide solution. The mechanism. The reaction proceed by SN2 mechanism I negative ion being the attacking species and the constituent the best method for introducing the iodine onto the aromatic ring. Third point is replacement by fluorine, Ball's-Skyrman reaction. For replacing the diazonium group by fluorine, the diazonium salt solution is treated with fluoroboric acid HbF4. When diazonium fluoroborate ARN to positive BF4 negative get precipitated, the precipitate is filtered, washed, and dried to isolate the fluoroborate. Diazonium fluoroborate are relatively stable compounds. The dry salt on heating decompose to yield the aryl fluoride, boron trifluoride, and nitrogen. The reaction known as the Ball's-Skyrman reaction mechanism of reaction further proceed by an SN1 mechanism reaction. Fourth point is replacement by OH. On warming an aqueous solution of diazonium salt, the diazonium group is readily replaced by OH to yield a phenol. Mechanism. The reaction proceeds by SN1 mechanism as given below. The aforementioned reaction takes place slowly even on allowing an ice cold solution of diazonium salt to stand. That is why diazonium salt solution are used for further reaction immediately after their preparation. The phenol formed in the reaction can couple with the diazonium salt to form azure compound. The coupling reaction is highly suppressed in strongly acidic solution. As such, the formation of phenol is best carried out by slowly addition the diazonium salt solution to the large extent of boiling dilute sulfuric acid. Synthetic utility. The above method is very useful for preparing phenol which are otherwise difficult to obtain. M-bromophenol may be prepared from nitrobenzene as follows. And the next point is replacement by NO2. This is carried out by decomposition diazonium fluoroborate with sodium nitrate solution in the presence of copper powder. Copper powder. Synthetic utility. The reaction can be used for introducing nitro compounds replacement by aryl group. Gomberg-Bachmann reaction. Many diazonium salt react with the other aromatic compounds in an alkaline solution to furnish compound in which the diazonium group has been replaced by aryl group. The next is replacement by arsenic acid group ASO3H2, which is the Bard reaction. This is carried out by decomposition of sodium diazonium salt with sodium arsenite in the presence of copper salt. And the next is replacement by hydrogen. Replacement of diazonium group by hydrogen can be best carried out by the following diazonium salt solution to stand in contact with hypophosphorus acid, preferably in the presence of cuprous ions. The reaction may be represented as shown below. Synthetic utility. This reaction affords a convenient method for removing NH2 or NO2 group from an aromatic ring. The complete process involving diazotization of an amine and subsequent reduction of diazonium salt. Replacement of diazonium group by hydrogen is called deamination. This can be a useful step in many synthesis reaction in which nitrogen atoms are retained in the product. Ninth is reduction to hydrazines. No loss of nitrogen on reduction with reducing agents such as stannous chloride and hydrochloric acid, sodium bisulfite or sodium sulfite, diazonium salt are reduced to hydrogens. Free hydrogens can be obtained from its salt by reaction with sodium hydroxide. Coupling reaction. A very important group of reaction of diazonium salt involve the reaction of diazonium ions acting as an electrophilic agent with aromatic compounds containing powerful electron releasing substituents such as OH, NH2, NHR, NR2. Reaction known as coupling leads to the formation of compound called azure compound form having the general formula ARN double bond N with attached with benzene ring J, where G is a substituent such as OH, NHR, NH2, NR2, the etc. As the compounds are strongly colored compound which constitute a group of dyes known as dyes. It may be noted that the nitrogen of the diazonium group is retained in the product and the reaction generally takes place in para position with respect to the substituent present on the aromatic ring being attacked. However, if the para position is already occupied, the attack occurs at ortho position. Mechanism. The mechanism of coupling involves the usual electrophilic aromatic substitution in which the diazonium ion is the attacking reagent as follows. It may be pointed out that the diazonium salt is uh, it may be pointed out that the diazonium ion is very weakly electrophilic. This is why it can. The mechanism of coupling involves the usual electrophilic aromatic substitution in which the diazonium ion is the attacking reagent as shown below. It may be pointed out that the diazonium ion is very weakly electrophilic. That is why it can attack only very reactive aromatic rings, that is rings which contain strongly activating substituents. However, if the electrophilic character of the diazonium salt is increased by introducing electron withdrawing substituent like NO2 in the aromatic ring of the diazonium ion, coupling may take place with even less reactive aromatic compound. Choice of the experimental conditions. An important factor to be taken care of in coupling reaction is the choice of suitable experimental conditions. The reaction conditions should be such that coupling takes place rapidly and the possible side reactions such as the reaction of diazonium salt with water itself to form a phenol and the coupling of the phenol thus produced with diazonium salt are prevented from taking place. The most important reaction condition which require to be regulated is the pH of the reaction medium. This is illustrated below in case of coupling with phenols and tertiary amines. The next is coupling with phenols. Penetrated with phenols in weakly alkaline solution, diazonium salt undergo coupling to form hydroxy azo compounds. Mechanism. The mechanism of the reaction involved the electrophilic attack of diazonium ion on the phenoxide ion. Role of pH in the coupling reaction. The choice of optimum pH range to be employed in this reaction may be understood in terms of the respective equilibria involving diazonium ion and phenoxide ion. It may be recalled that in the presence of the OH negative ion, the diazonium ion occurs in equilibrium with diazohydroxide and the diazotate salt. Both diazohydroxide and diazotates are not electrophilic, therefore do not take part in coupling. This means that in strongly alkaline reaction medium, high pH value, the concentration of attacking electrophilic species would be low. In other words, a high concentration of attacking reagent requires the solution to be acidic, low pH value. Phenol in aqueous solution occurs in equilibrium with phenoxide ion. Due to stronger electron releasing effect of O negative than OH, phenoxide ion is more reactive towards electrophilic attack, but the equilibrium depicted above would shift towards phenoxide ion only in an alkaline solution. Thus, a higher concentration of phenoxide ion require the reaction medium to be alkaline high pH value. In the light of the above discussion, it is evident that the optimum pH range for the coupling reaction would be a result of compromise. The optimum pH range for the coupling of phenol has been found to be 9 to 10. This means that coupling of phenol is best carried out in slightly alkaline solution. The next point is coupling with tertiary amines. Coupling of diazonium salt with tertiary amines takes place in slightly acidic solution to form dialkyl amino acid compounds. The mechanism of the reaction is role of pH. As I already explained, high concentration of diazonium uh, ion require the reaction medium to have a low pH value, but at low pH the amine will be largely protonated. Now the protonated amine, due to positive charge, it is quite unreactive toward electrophilic attack. This means that in coupling reaction the amine should be dominantly in the free form, which is possible only if the reaction medium has a high pH value. As a result of compromise between the pH range requirement of diazonium ion and the free amine, the actual pH range employed in the coupling of tertiary amines is 4 to 5. The reaction medium is slightly acidic. Next is reaction with primary and secondary amines. Primary and secondary amines generally react with diazonium salts in mild, mildly alkaline solution to form colorless diazoamino compounds. In this reaction, attack of diazonium ion takes place at amino nitrogen rather than on the ring. However, the diazoamino compound thus formed undergoes rearrangement when heated in acidic medium to form the colored azo compound. Synthetic applications of diazonium salts. In introducing the chemical behavior of the diazonium salt, it was stated that diazonium salt can be employed as very useful intermediates in the synthesis of a number of aromatic compounds, many of which are difficult or impossible to synthesize by other methods. The preparation of oxalic acid and B-bromophenol and 1,3,5-tribromobenzene were cited as some examples of the synthetic utility of diazonium salts. A few more examples are further illustration. Synthesis of M-bromotoluene from toluene. In the above synthesis, the conversion of constitute the key step. It is based on the fact that NHCOCH3 is much stronger OP director than CH3 group. Since the para position is already blocked, bromine is introduced at odds of position with respect to NHCOCH3. It's all about its synthesis. Synthesis of p-bromobenzonitrile from nitrobenzene. Nitrobenzene is taken and it is treated with the hydrogen gives aniline. Again, it is treated in CH3CO2O. It gives NHCOCH3 on the benzene ring. Again, it is treated with Br2. It gives Br at the para position and or at the ipso position NHCOCH3. Again, it is treated with water in the acidic medium gives NH2 at the ipso position of the benzene ring and Br at the para position. Synthesis of 3,4,5 tri iodonitrobenzene from p-nitroaniline. If further required, the nitro group may be removed by conversion into NH2 group followed by diazotization and reduction to get 1,2,3 tri iodobenzene. Thank you.